that quantum mechanics has something to say about agency. I am well aware that I am not the first person to make that claim, so I want to distinguish what I'm going to be saying from what other people have said. There are famous claims, for example, that conscious agents collapse the wave function. That is not going to be my claim. In fact, if that is true, what I'm going to say today is going to be irrelevant. I have to assume that's false. There are also claims that consciousness results from quantum mechanical processes in the brain. I'm going to remain completely agnostic on that question. And there's also a claim from Eddington, and I've actually got the quote here. With the advent of the quantum theory, physics is no longer pledged to a scheme of deterministic law, and so science thereby withdraws its moral opposition to free will. I'm going to argue, well, first of all, I think history has not been kind to that claim, both on the physics grounds that the evolution of the wave function is deterministic, and on the philosophy grounds that being instructed what to do by a random number generator doesn't really count as agency. And indeed, my talk today is going to be arguing that this has it backwards, that in some sense, quantum mechanics makes the behavior of agents not less predictable, but more predictable. And I'm going to start off with the same somewhat cowardly caveat that Sean started his talk with, which is that this is a work in progress. And I'm also going to add to it that this is somewhere at the intersection of quantum information theory and philosophy, and I am not really a quantum information theorist, and I'm really not a philosopher. But what I am is amongst friends, so I hope you will take this in that spirit. And I'm going to start off, in fact, on somewhat solid ground with physics. If you are not a physicist and you've not seen anything before, then even if you don't believe anything else I say in this talk, I hope you'll find the first part of the talk fun. So let's start with the sort of classic physics, quantum mechanics object, which is an interferometer. And the way they work is you send a laser beam in, it bounces off two mirrors, and they coherently interfere with each other so that all the light exits the final beam slitter to the right, none of it up. And that is true despite the fact that if you shoved an absorber in the way on any one of the arms, there would be no interference, and some of the light would exit up while the rest of it exit rightwards. And that's true for either path, but somehow when you add them together, you get complete destructive interference upwards, complete constructive interference rightwards, and all the light exits right. If you think that is a weird quantum phenomenon, you are wrong. This is a classical phenomenon. It's just a wave phenomenon. You can do it with water waves. When it becomes a weird quantum phenomenon is when you have both waves and particles, when you attenuate your laser so that there's only one photon going through the apparatus at any given time. And the weird quantum phenomenon is that even though there's only one particle going through the apparatus at any given time, one photon, you still get the interference pattern. However, you can kill the interference pattern by measuring which arm the photon took. And so now, so for example, you could have a mirrored detector on the bottom right. And now let's just be super pedantic about what happens next. There are four possibilities. When you measure which arm it goes down, you can either find that the detector says it went down the bottom arm, or on the bottom it didn't go down the bottom arm. And since you've destroyed the interference pattern, it can appear either up or rightwards at the end. It exits the up port or the right port. And in particular, even though if you measure the particle, you can find that it didn't. The detector cannot measure it to have gone down the right arm, and yet the photon can still exit upwards because you've destroyed the interference pattern. This is a somewhat strange phenomena, and Elitzer and Weidmann found a particularly vivid way, a way to make it, the sort of strangeness of it, particularly visceral, with a rather nice example. And the nice example is they imagine the following task. You are given a pile of hypersensitive bombs, or maybe duds. You're not really sure. They look the same, the bombs and duds. And the only difference between a bomb and a dud is what they do when a single photon impinges on them. A dud just reflects the photon. Nothing weird happens. But a bomb, true to its name, explodes. So that's the rule. And your job is, from this pile of hypersensitive bombs and or duds, you're required to give me a bomb, something that's definitely certified to be a bomb, a live bomb. If I asked you for a certified dud, that would be an easy thing. You just fire the photon off one of your candidates, and if it explodes, well, too bad, try again. And if it doesn't explode, then you have a certified dud that's definitely a dud. What if I ask you for a certified bomb? Well, the problem is pretty obvious. Once you fire a photon off the candidate, if it doesn't explode, well, no good, that's a dud. And if it does explode, then it was indeed a bomb, but you have not produced a live certified bomb. You've atomized a live certified bomb, and that is against the rules. So I think you will agree that classically this is an impossible task. And now where our pedantry from the last consideration of the interferometer is going to come in, is that it is not a quantum mechanically impossible task. In fact, this is what you want to do. And I think it's pretty clear, given what I said before, why this is what you want to do. So first of all, let's imagine that the bomb is in fact the candidate is in fact a dud, in which case you're just going to get exactly the same story as you had before. The dud doesn't in any way detect the photon just bounces off, and you get complete constructive interference at the right port, complete destructive interference at the top port. The photon never exits upwards. Okay, what about if it's a bomb? Okay, well now we have a slightly more complicated situation. There are 4 possibilities. Bomb, by exploding or not exploding, measures which path the photon took through the interferometer. If it finds that it took the bottom path through the interferometer, well, bang, you've just exploded your bomb. No good. But 50% of the time, the photon will take the bottom path through the top path through the interferometer. 25% of the time, it'll emerge from the right port, there being no interference, and 25% of the time, it'll emerge from the top port. Now, the bottom right one is the really interesting case. Here, there has been no explosion, and yet the bomb has emerged, the photon has emerged from the top port. I will just remind you that in the dud case, the photon always emerges from the right port. So what do we infer from the fact that that even though there was no explosion, the photon exits from the up port? What we infer is that we in fact had a bomb. We have successfully completed the Elitzer-Weidmann task. We have produced a certified live bomb using the power of quantum mechanics. Okay, this is great. One slightly unsatisfactory element is that it's wasteful. You produce 2 explosions for every certified live bomb you create. You can actually do better using the quantum Zeno effect. Famously, if you have 2 filters and they are at 90 degrees to each other, the probability they transmit is cos squared of the angle between them. So if one starts vertical, the other starts horizontal, there is no transmission. Weirdly, if you shove in a filter in the middle that you might imagine could only decrease the absorption, absorb things, could only decrease the transmission rate, the transmission rate then goes up. Just as weird that by putting an absorber in the middle, you increase the transmission rate, as the fact, and it is the same fact, that you sometimes get photons emitted upwards even by adding an absorber into your interferometer. And in fact, the more filters you add, the higher the transmission rate. The reason is that the probability of being absorbed is proportional not to delta theta, but to delta theta squared. That is the central, probably the central weirdness of quantum mechanics, is that the absorption rate is not proportional to delta theta, it's proportional to delta theta squared. That's what gives rise to Bell's theorem and all these other weird and wonderful facts. And in particular, that means that if you have n absorbers, the angle required between them goes like 1 over n. So you end up having a probability 1 over n squared of absorbing n times. 1 over n squared times n goes to 0 as n goes to infinity. The transmission rate goes to infinity, known as the quantum Zeno effect, or in other contexts as the adiabatic theorem. Okay, so you can combine these 2 ideas, which in this context means going from there to there, and you can in fact have the quantum. You can in fact have a perfectly efficient, or approaching perfectly efficient, as this tower of interferometers gets infinitely large. You can have a perfectly efficient bomb detector that never blows up bombs, but nevertheless produces certified bombs. Okay, great. So that's a bomb. Pretty soon after these ideas were developed, people started hunting around for other things other than explosives you could put in the right-hand corner. And one of the most interesting proposals by Mitchison and Josa is that you could put a computer. And I should warn you that from now on in the talk, we're going to become increasingly untethered from engineering considerations and restricted only by the laws of logic and of physics. For a start, this can't really be a Dell computer. This needs to be a quantum computer. But it basically works exactly the same principle as the Weidmann bomb. It either runs or doesn't run according to where the photon goes. OK, so what's the computer doing? It's implementing some unitary. And the question you're going to answer is, does that unitary transformation output on the state phi an answer 0 or an answer 1? And then we can just do exactly the same thing as we did with the Weidmann bomb, this time in equations for people who like equations. And what you see is that when it outputs the answer 0, you get complete constructive interference. The computation might as well not have happened. It's like a dud, and you get everything emerging from the right. But sometimes, one of the 4 possibilities, when the answer is 1, is that the computation didn't happen. You took the top path, and yet you learn that the answer you would have got, had you done the computation, is 1, without ever doing the computation. It's exactly analogous to the way the Weidmann bomb worked. OK, so you can do a counterfactual computation. You can, in some sense, learn the result of the computation without ever doing the computation. And again, we're going to do a sort of Zeno version of this to make it perfectly efficient. Now, this is sort of great little literature on what's called counterfactual computation that ends with the sort of discoverers in this sort of review paper sort of complaining that it's not really good for anything. The reason being is that there had initially been hopes that you could maybe use this to not actually have to build a quantum computer, or maybe it could run faster. But anyway, none of those things are true. It doesn't help you with decoherence. You still need to build the quantum computer. It still needs to work. Otherwise, it's not going to do its job in the interferometer. It still needs to be protected from decoherence. Basically, the review article ends with the question, who cares? And the point of this talk is that there is, in fact, a reason you should care about whether the computation happened or not. And that's if what the computation is doing is simulating your thought process. You care. So the rest of the talk is going to be considering this possibility, that what the quantum computer is doing is simulating you. 2 quick assumptions I'm going to make. First of all, if the Copenhagen interpretation is right, this doesn't make any sense. I'm putting a conscious observer in a superposition. It'll immediately collapse. So I'm going to have to take a no-collapse interpretation of quantum mechanics. The other assumption I'm going to have to make is that the amount of consciousness, the quantity of consciousness, if you simulate a conscious observer in superposition, is given by just Born's rule, basically. It's given by the amplitude squared. Actually, everything I'm going to say goes through if you come up with some reason why it's less than the amplitude squared, but it's just not going to be more than the amplitude squared. OK, and then in fact, I'm going to do exactly the same as with the quantum Zeno. This is going to be the setup that I'm going to imagine. OK, so now we're getting on to philosophy. What is this good for? What does this actually tell us about agency? And since we're now into the philosophy part, I'm going to sort of quote some other FQXi members, just so that if we go down, we all go down together. I think that there is a position I've often found pretty compelling, is a sort of classical notion of compatibilism, where you say that even deterministic agents are unpredictable. And this really has 2 components. The first is the claim that to accurately simulate an agent requires simulating their thought process accurately. Seth Lloyd would talk about in fact, did talk about the Hartmanis-Stearns theorem, the time hierarchy theorem, that says that in general it's impossible to predict what a conscious agent will do with a procedure that is less sophisticated than simulating the conscious agent. Scott Aronson said the problem of predicting your behavior is U-complete, which is, I think, a pretty Scott-complete way of stating it. OK, that's step 1. You've got to do a high-fidelity simulation of an agent in order to predict what they're going to do. Step 2 is that a sufficiently high fidelity simulation of an agent would be just as conscious as the original. Radford Neal said the simulation the predictor conducts in order to predict your choice will, if you accept a functionalist view of consciousness, which I suppose I do, create another conscious being, and you have no way of knowing that you are not this being. So this provides quite a nice sort of picture of agency and how we can come to believe that we have agency even in a deterministic world. Because if you want to predict what somebody's going to do, and therefore rob them of your agency, you have no option but to create a new agent and imbue it with agency who lives in the computer you're using to simulate them. That's the classical story. It seems like quantum mechanically, it's no longer so obvious that you can make that phenomenon. In particular, it at least appears as though using counterfactual quantum computation, perhaps I should say using counterfactual cognition, you can simulate what somebody's going to do, you can predict what they're going to do without simulating them. And now I'm going to tell you that that is exactly half true. I proved a theorem, other people have their theorems, I have mine, and this is the theorem. Counterfactual computation can tell you what the answer is on one branch. You can set it up so that it can tell you what the answer is if the answer is 0 without having to run the computation. So long as, if the answer is 1, you have to compute them many times. You have to compute that branch many times. In fact, there's a multiplicative inequality. You can set up a counterfactual computation so that n0 is as small as you like, but only at the cost of making n1 very large. So n0 being the number of times you simulate the thought process, weighted by Born's rule, in order to arrive if the answer is 0, so long as n1, the number of weighted computations you have to do in order to arrive at the answer if the answer is 1, is very large. You can only predict without simulation half the time. If the answer is yes, let us say, you can predict without simulation. If the answer is no, you have to simulate them many times. But for some applications, that's exactly what we want. And let me provide a somewhat fanciful sci-fi scenario here. Leading a happy life is not easy. Some apparently good decisions lead to great sorrow. Sometimes superficially bad decisions lead to great life satisfaction and meaning. It does not seem unreasonable to believe that to truly know what decisions to make, there is no method that is less complicated than simply making those decisions, leading to one's life, and seeing what happens. That, however, algorithm has a problem, which is that if your decision turns out to be very bad, then by the time you get to the end of your life, you have already suffered all the sorrow that derives from your decision. However, there is a solution, and the solution is to counterfactually compute the outcome of your decisions. And as I said, there's an inequality, but you can set up the counterfactual computation in such a way that if the outcome of your life decisions is happiness, you compute it many, many times over. And if the outcome of your life decision is sadness, then the weighted number of computations you perform tends to 0, which seems to be what we're after. And there is the, just for people who like circuit diagrams, that's the circuit that performs that for you. Or if I mean, you'll notice a structural similarity between this example and the previous example, now scaled up in our ambitions. You plan to create an entire universe, and you plan to create only those universes that are, not only those universes that are perfectly good, but also all universes that are better to exist than not to exist, in the words of FQXi member Don Page. And the question is, how do you know that the universe you're going to make is net positive? Even if you're omnipotent, how do you achieve functional omniscience about the consequences of your actions? And it seems like you basically can't, given some time hierarchy theorems. You just can't do it, classically, because in order to simulate to know whether a universe is net positive, has more good than evil, you are going to have to simulate those universes and see how it goes. But of course, you can do it using counterfactual cognition if the meta-laws of the universe you're using to simulate this in are quantum mechanical. Okay, so there's just some brief applications of counterfactual cognition. Let me end with two physics points. First of all, notice quite how strong a ability this is that quantum mechanics provides you with. You can essentially impose any boundary conditions you like at the end of the universe. This is not, often we post-select on some quantum, on some final boundary conditions, but what we mean when we post-select is we do our quantum experiment, we measure it at the end, and if we don't like the answer, we just throw it away and run the system again. That is not what we're doing here. What we're doing here is ensuring that if you weren't going to get the answer you didn't like, then in a wave function weighted Born sense, you never instantiated that possibility to begin with. You only simulate those branches that lead to the desired outcome, except with measure 0. The second point is that, sort of inspired by this analysis, you can, in fact, sort of redo, there's a whole field of quantum query complexity, you might be inspired to redo quantum query complexity with now a different counting of the number of queries. Usually you count, in quantum query complexity, you just sort of count the components in the circuit. Sort of, for example, in Grover's algorithm, you'd find that there are root n oracle calls required to determine the answer to a certain question. And just every time you come across in your quantum circuit a certain component, that counts as one query. That is not the right algorithm here. That is not the right counting here. The right counting here is instead of counting each component once, you count each component, if it is a controlled query call, you count each component by the square of the amplitude with which it's called. And so you can just ask a pure physics question, which is how does that affect the counting in quantum query complexity? For example, how does that affect the root n scaling in Grover's algorithm? And the answer may surprise you. That's it. Any questions?